Okay, so most of you got all your exams done. Yeah. Yeah. Yeah, I know there's one student who has her exam like right now, I guess. So she would be joining towards the end. Yeah, I don't quite understand how that wound up happening, but you know, she said she has an exam. So, but the rest of you are done, right? So you can actually pay attention today. You have nothing else to do. Yeah. So as I said, what I'm planning to do today is actually shift the usual thing. I want to do more technical stuff in the beginning, and then we will end with a discussion of your reflections and any open discussion. That's the way we'll wind up doing, so that it'll be more fun. Okay, so let me see if I can. Yeah, I should be able to share, right? Okay, can you see this? Yeah. So what we are planning to do, as I said, is actually I'm going to play on TensorFlow, sort of talking about machine learning and supervised learning, which is kind of cute because it sort of takes off from where we left the last class. Then I will, depending on how that goes, I have a couple of other things that I wanted to bring up, infinite horizon rewards and money and utility. If I get to do that, I'll do that. And then in the second part, we will look at your reflections and also, you know, any questions you have, etc. So in fact, you'll see that your reflections actually have been processed into word clouds. So we'll be able to look at them. Okay. So the other thing, so let's get started. This crowded thing is what we were looking at the end of last class. And the point I was trying to make, if you can remember, it was 2 weeks back. So I wanted to sort of redo it a little just to remind you. This idea of learning patterns from data is not, it's a what is known as a highly underspecified problem. It's an underspecified problem, which is why I asked you, if you have 2, 4, 6, and 8, then what is the next? What is the next number? And you know, most of you would like to say 10, but that is because implicitly you are connecting those points with a line, and then so you're extrapolating the line, and then you are saying the next one has to be 10. If all you are doing, in some sense, you can think of learning as this stuff, 2, 4, 6, and 8. This is your training data. And you have a set of what are called hypotheses. A hypothesis, for example, might be what is the function that fits this data as closely as possible. So if you are talking about, essentially, if you have some bunch of points, right? I am essentially trying to look for a function that fits these points. Okay. Now, of course, a function, if you're thinking even in terms of two-dimensional functions, a function can be many, many different things. Function can be a line. That's a linear function. That's like the first thing that comes to your mind. Okay. So in general, actually, when you see a bunch of points, you think I'll fit like a line. That's a line. Now, when I did that, what I'm essentially doing in my head is what is among the infinite number of lines that I can draw in this plane, which is the line that has minimum squared error from all the points. Do you understand what I'm saying? Right? So for example, why is this a good line? Why not this line? Let's say, why not, let's say this line, because these were the points, remember, right? These are the points. Okay. And I said, this is a good line. This is line 1. And here is line 2. Now, why is line 2 not as good? Because for line 2, each of these points are much farther away. That's one. So you basically are dropping perpendiculars from each of the points onto the line. And then you're taking these distances. If they all fall on the line, those distances will all be 0, right? You see that? Okay. So, and if you then, sometimes what happens in this particular case is some are falling this side, some are falling this side. So there could be positive as well as negative distances. That's why you just square the distances and add them up. Okay. And then you are saying among all the lines, y equal to mx plus c is a line. Do you understand? Remember that from your, like the old grade school math, y equal to mx plus c. I just need to find m and c. Give me the line with the correct m and c such that it winds up being having the least distance from all these points. Do you understand what I'm saying? So that's the optimization problem you are doing. That's the optimization problem you're doing. Okay. So among all hypotheses, in this particular case, I'm looking hypothesis as lines. Okay. Find the one that has the best fit to the data, to the training data. Because these are the points that I've already given you. Okay. So this is basically what you're doing. And once I find the hypothesis, once I find a line, then I can tell you for the points that I haven't seen what their value should be. Because every point on this line is supposed to be a data point. That's what you are thinking. Okay. Now here, this one, basically, this is an optimization problem. It's optimization because you are essentially trying to look at this whole set of lines and find the line that has the lowest squared distance from all points. It's also continuous optimization problem because the m and c can take continuous values. And each of them will correspond to a different line. So if you actually try to do simple idea of optimization would be, I'll take each line, look at how far it is from the value, points, and then I'll sort them all together and then find the best line. You will die because you have infinite number of lines. So whenever you have to do optimization in continuous space, who will help you? Who will help you when you have to do continuous space optimization? Calculus. That's the only game in town. In fact, I was reading your reflections, and somebody, I forget who, said that the day we discussed gradient descent, which is basically a way of finding optimization, the day before that, apparently the student learned about gradient in the class, and then they came to my class, and then they found, oh, so it looks like calculus has actual applications. which I thought was like the understatement of the century, right? Because ever since, which is great. I mean, in some sense, that's the reason to teach this to first year students, right? I mean, basically pointing out that the stuff that you do in your classes has actual uses, okay? But I mean, Uncle Newton was not a bozo. I mean, essentially, he came up with calculus, which just is useful everywhere. Okay, and in particular, calculus is great for optimization because you essentially write this, finding the fit of a line, the fit of the line to a set of points. You can write this essentially as an expression, which will be changing based on the values of M and C. And then you are essentially going to find the best value of M and C by taking the derivatives and equating them to 0. Okay. How many of you actually heard of line fitting in your grade schools? That's what you did. When you fit a line in grade school, this is what you're doing. You never asked yourself, why am I fitting a line? Did somebody tell you that these points were produced by a line? No. You just decided, oh, why not a line? In fact, everybody tries lines first. In fact, there's this beautiful point that linearity assumption, those of you who are engineers will keep hearing about this idea called linearity assumption. That means somehow the process that you're trying to model is linear. Linear means in the end, it is y equal to mx plus c. If it is a multi-dimensional place, it will be y equal to m1x1 plus m2x2 plus m3x3 plus m4x4, blah, 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 plus c. Okay, so it will be just a single hyperplane. The idea is that you try to look for lines because A, it is easy to do. And strangely enough, many things in the world seem to work out if you actually look for lines. It's sort of mind-blowing. Why should it be that what is easy to do mathematically is also more or less describing the world you live in? That's actually an interesting meta question that you can actually ask yourself. And in fact, you can ask also yourself this other question of why should it be that math, which we invented, is useful for describing the world that we didn't invent? It was there, right? Universe was there before you came along. Do you understand what I'm saying? So in fact, there is a beautiful paper by Eugene Wigner called The Unreasonable Effectiveness of Math in Physical Sciences, is what he said. Okay, there's no obvious reason as to why something that we just basically separately invented wound up being pretty darn good in modeling the world we live in. And in having that, after Wigner said this, people started talking about unreasonable effectiveness of linearity assumption in describing our world. Because forget about all math, just the simple part of the math, which is looking only for lines, somehow seem to work fine most of the time. Do you understand what I'm saying? And then, of course, there is a third kind of unreasonable effectiveness that people have been talking about nowadays, called the unreasonable effectiveness of data. So in general, it's become like a fad. Ever since people started talking about unreasonable effectiveness of math, now you can just say anything seems to be working too darn well. You can say unreasonable effectiveness of that thing. Okay, because there's no good reason why linearity assumption should work, but it seems to work. Okay, it's so much so that there are all sorts of jokes about linearity assumption. Let me see if I can keep it, and let me see if I can add a line. Let's see. New slide, new slide, new slide, new slide. Oh, this is not layout. Good. Now I have enough pages. I can write whatever I want. So there is so when you have a bunch of points like what we had before, and you fixed a line through this, right? So the question is it always possible to, suppose I give you a line, points like this, let's say, suppose I give you points like this. That's my points. Can I fit a line through this? Of course you can. I mean, many of you realize what this is, right? What is this? A sine wave.
Sine graph.
Right? Okay. Can you fit a line through the sine wave? Yeah, of course. What do? You say, this is the best line. Of all the lines, this is the best line. Then everything else is noise. In fact, people have said that psychologists, somebody said, I think one of you was the psychology major. There's a joke about psychologists that they try to look for lines in the data. And so basically they'll say, this is noise, that's noise, and everything else basically. So basic idea is, why do you think, let's say, if I give something like that data, you feel it's okay to look for a line like that? Because you think the reason these points are not falling on the line is because there's some noise in measuring the actual position of those points. Everything else falls on the line. So this is the best line. So really line is the reality and the points are just noisy measurement of reality. You understand what I just said? Now, if you're into believing that there is something called noise, then you can delude yourself into thinking, well, this sine wave, it looks like a sine wave, but really this is the reality, and there's just big noise in measuring the points in various places. Okay, so the first thing I want you to understand is that, going back to this 2468 thing, you said the next is 10, like right away, because most of the time we look for lines. But my second question is that if I really say you don't have to look for just the best line, you can look for the best polynomial, where line happens to be the first degree polynomial. You guys remember polynomials of degrees? Like x power n, where what's the highest value of n such that x power n is there in your expression. And if n is 5, then it's a fifth order polynomial, right? In linear, anytime you have a line, it's a first order polynomial. Suppose I say I would not mind looking up to fifth order polynomials. Right? So then I'm looking for ax power 5 plus bx power 4 plus cx power 3 plus dx square plus ux plus c. And I'm trying to find a, b, c, d, u values. Okay, so I can do that. And if I do that, in essence, actually, you find that you can indeed fit a fifth order polynomial. In this case, this is actually a fourth order polynomial that goes exactly through these lines. That goes exactly through these lines. So as far as you are concerned, if you are looking for best fit line, this is as good a best fit as this. Both of them have zero error for training data. Do you understand what I'm saying? Both of them have zero error for training data. So why do you like this more than this? Because you have a bias. You believe that in the world that you live in, if in fact a lower polynomial fits the data closely, then it's probably more reflective of the actual process that generated the data than the higher polynomial. Do you understand what I said? Okay, how many of you understand this point? Let me repeat that point, that if you can fit an nth order polynomial through k points with zero error. That means the polynomial passes exactly through these k points. Okay, then you can also fit any mth order polynomial where m is greater than n. Do you understand what I'm saying? So if a simple story works to explain your data, every complex version of that story also explains the data. If you can fit the line through the points, so can you fit a higher order polynomial through those points. There would be some higher order polynomial that can be fit through those points. Do you see what I'm saying? And because of which, the question then becomes, why are you, how many of you really believe that when the line is fit through the data, as well as a 15th order polynomial that can be fit through the data, you should go with the line? How many of you believe that? Just raise your hands. How many of you feel that that should be the way the world works? Because if not, if you don't believe that, then there is actually no end. If the 15th order polynomial can be fit, so can be a 19th order polynomial, so can be a 25th order polynomial. So what exactly is the story you're going to stick to? The curve that you are fitting through the data is the story you are telling about the data. Okay. If a simple story suffices for the data, then so can a complex version of that simple story. Do you understand what I'm saying? Okay, this brings us into this issue of bias variance trade-off. The reason you actually believe that we should go with lines rather than polynomials is because, first of all, you may just be looking for lines in the data. So if you're looking for the lines in the data, you will find lines in the data. Because as I said, you can find lines that the closest fit line to a sine wave, you can find it. Okay, so it'll always be, there'll be some error. Among all the lines, this is the best line. And you'll assume that the rest is just error, measurement error. So interesting thing is that this picture that I want to show you is, if you were to consider order of the polynomial, here, okay, and training error here, okay, and I will look at two issues. So I've been given points P1 to Pn, which are the n points that are the training data points. I'm trying to fit the best, first order polynomial through these points, the best second order polynomial through these points, the best third order polynomial through these points, and so on. Okay, and when I fit the best, then I take the mean square error of these points from that curve. That would be called the training data error. So in our example previously, this squared sum of these distances is the training data error. Because you realize that this is the best line. For the best line, the points are still not falling on the line. They're a little far away from it. So you take the squared sum of the distances of each of those points from the line. And that is the total error you have for this line. This is the training data error for your line. Now, as I increase the polynomial. That means I allow now second as well as first order polynomials, third as well as second order polynomials, and third, second as well as first order polynomials, right? If I allow this, then in essence, the best, so here is something. If I have a set S and I have another set which is S plus another set M. Okay, that means this set is a superset of this. And these are sets of hypotheses. If your training error among the best element in this set is, let's say, 10, do you not see that the training error among the best set of elements in this bigger set cannot be more than 10? Do you understand what I'm saying? So imagine I have like 10 of you. Okay, the best IQ among these 10 of you I have is, let's say, 125. Okay, I added to this 10 set another 5 set, and another 5 more students from the street I put in. Then I'm asking, what's the best IQ I can get among this bigger set? The best IQ in the bigger set cannot be less than 10, less than 115, because you guys are still part of that other set. If on the other hand, ASU freshmen tend to be somewhat dumber than the random students passing by, random kids passing by on my street, then it can be better, right? It can actually be 150 instead of 115. It's the same thing here. The training error for the small set is a lower bound on the training error of any of its supersets. And as you increase the order of the polynomial, the sets are becoming bigger and bigger, sets of hypotheses. Do you understand that? So what that means then is, if I consider just the training error, maybe depending on the data, maybe the training error will start somewhere higher, but then slowly fall down. Eventually it will become 0. All that I'm saying is, irrespective of how complex and crazy the data is, I will be able to fit the curve to go through exactly those points. And this curve may be like a 75th order polynomial. Do you understand what I'm saying? So if I increase the order of the polynomial, that means if I allow for more and more complex hypotheses, then the training error can only reduce, because the set is becoming bigger and bigger. But my question is, what did I do just now? Yeah, but my question is, you somehow thought that, so you somehow think that in this particular case, what happened? There is something I'm doing. Okay. So I was trying to change my color, but anyway, so imagine between this and something like this, if you were to like this line, the reason you would be thinking you like the line is because you think the generating process is line and the points that are off of the line are just noise. And if you look for more and more complex hypotheses, they will fit to the noise. They will fit to the noise. If you fit to the noise, then your predictive power on data that you haven't seen is going to be bad. So how do I figure that out? Instead of, in addition to these points P1 to Pn, I have also been given points T1 to Tk, which is test points. These test points are never shown to the learner when it is figuring out what curve to pick. Having decided its curve, Then I take that, you tell me what your curve is, then I will basically plug in the X values of these K points, find out what your curve predicts as the Y value, take the error between your prediction and what the true value is, square them, add them. That would be called test error. Okay. The question is, I want you to think of, okay. Yeah. I want you to think of what happens to the error if, for example, the data, let's say the data was like this. Like that. Can you see that? So it's like basically line. But if I allow higher capacity, higher polynomial, the polynomial will nicely fit through this data. So there are like two options. One is you can just actually fit a line through this. The other is you may be able to fit a polynomial which looks like this. You might be thinking, where do I get this? But you played with graphing calculators, right? You can essentially get a polynomial to have any weird shape. Okay, so the question then is, why don't I believe this is the real story behind the data? Because I tend to think it's likely to cause more error in prediction. Which means if I were to actually start looking for, as this thing is going on, if I were to plot the test error for each of these polynomial sizes, the test error starts coming down in the beginning, but the intuition for you should be that it will start going up after a while. And when it started going up, then essentially imagine the original data was produced by 7th order polynomial. That you produced it by 7th order polynomial. Then up to 1, 2, 3, up to 7th order, the test error keeps going down. After that, the test error keeps going up. But the training error will still remain 0. Because if you are considering a 7th order polynomial, there will be an 8th order polynomial that will vacuously be able to go through all the points of a 7th order polynomial. Okay. So what you expect essentially is the test error will come down first and then start going up. And the best hypothesis would be this. If you had the chance to figure out what is the best curve to fit to my data, then it would be this. Okay. This particular phenomenon is called the bias variance trade-off. And this idea of order of the polynomial, you can think of it as the capacity of the learner. The capacity of the learner is how much of a complex polynomial it can fit to the data. Okay. Okay. So the other thing, by the way, what is happening in this region? This region, you say it's overfitting. Have we heard of the word overfitting? I mean, have we mentioned it here? Overfitting essentially means you are learning the noise in the data. This leads us to a very interesting point. Compression versus learning. You guys have heard of compression, right? Right? I mean, your music is MP3 compression. Your videos are MP4 compression. Your zip files are compressing files such that it will take less space. When you talk about compression, you talk about generally lossy versus lossless compression. The zip file, is it lossy compression or lossless compression? You guys have used zip, right?
It's lossless, right?
It better be lossless. Right? It better be lossless because you carefully typed all your notes and you say, let's reduce the amount of space taken, and so you zip it. And then when you unzip it, half of the files are gone. Or every other character has got garbled. That's no fun. You understand what I'm saying? So how many of you have tried to zip a directory containing JPEG files or directory containing videos? Does it reduce the size?
Technically, yes, but not really.
Technically, it doesn't actually. Oftentimes, if you zip things like videos and audio, the zip file size can be bigger than the original size of the folder. If in fact people look for lossless compression on audio and video, we will be dead. We'll be dead. Nothing will actually work for us because essentially, while you want lossless compression for files, ASCII files, text files, you cannot actually get lossless compression which is effective for videos and audios because in fact there is not enough of a redundancy there. Okay, so instead what you do is you do lossy compression. Okay, so once you do a JPEG, how many of you realized, for example, that in cameras, I don't know actually, I don't know if you have cameras, but cameras can store images in JPEG, or they also offer to store it in the RAW format. How many of you have realized this? What's the difference? Once you do JPEG, it's basically lost some of the quality, some of the actual pixels, correct values of the pixels in the picture are gone. They will never come back. Do you understand what I'm saying? That's lossy. Okay, now in general, compression, if you could have both lossy and lossless compression, and you can get lossless compression without actually paying much of a price. That means lossless compression will also reduce the size of your image folder. Would you prefer lossless or lossy compression? You would prefer lossless. The only reason you're stuck with JPEGs and MP3s is because you can't do lossless compression for images and lossless compression for videos. Okay, but in general, compression remembers the data exactly, which means it will remember every little kink in the data. Do you understand what I'm saying? If you, on the other hand, are trying to learn future, then you are better off deliberately losing quality on the training data because the best compression methods will be here. The training error is 0. But we are saying the best learning methods are somewhere in the middle. Do people understand this? These are very key points. It may or may not make sense, but your semester is over. Why do you care? You should try to, mess with your minds for a bit. Okay. So compression and learning are two very different things. Memorization and learning the subject are two very different things. If you memorize what I am saying, you will just try to do all the mistakes I am doing. You will sound exactly like me. But if I ask you to only reproduce what I told you, you will be fine. If on the other hand, on the exam, I come up with a new question, then you'll say, I didn't know this. You never talked about this. Learning is all about future. Compression is all about current. I just basically have this too much space, too much data. This data is taking too much space. I'll just compress it. But learning and compression are very closely related. You see what I'm saying? In essence, when you fit a curve to a huge number of points, you have compressed those points. Do you understand that point, by the way? Let me see if I can make that point again. So suppose this is the number of points I have. To store all of them, I have to write x, y values for all of these. If on the other hand, if I fit a line to this, that line's equation will be y equal to mx plus c. All I need to remember is m and c. I compress the heck out of the data. You see what I'm saying? But in this particular case, this is not a particularly good compression because the points won't be exactly reproduced. If you really want to exactly reproduce them, then you need to learn this curve, whatever, which will go through every one of the points. That would essentially be y equal to m1 x1 x power 17 plus m2, maybe m17 x power 17 plus m16 x power 16 plus m15 x power 15 plus blah, 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 m1 x power 1 plus c. It's still better than remembering all the points. Learning is connected to compression, but in doing learning, you're not looking for the perfect compression. You're actually looking for something, the perfect compression for the data. Sorry. Perfect compression for the data is here, but the best hypothesis about future may well be somewhere here. What has any of this got to do with the things that you guys care about, which is neural networks, right? Let me see if I can do this. More things to add. Okay. What does this got to do with neural networks? It turns out, in a minute, we'll see this on the TensorFlow thing, that if I put, let's say I have x1, x2, x3, x4, w1, w2, w3, w4 output. This is nothing but w1 x1 plus w2 x2 plus w3 x3 plus w4 x4. Apply this to, in this unit, basically this unit, what every neural network, a neuron, basically what it does is it takes the inputs, multiply them with the weights, okay, and then there is a thresholding function G, which we talked about, right, during the semester. So basically, it's a nonlinear function that you apply into W1X1 all the way up to W4X4. And whatever is coming out of that is being given out as the output. What that means is if you trained a single layer neural network, in essence, it finds the best line that goes through the data. Okay. Now, the interesting thing is I don't need to just train a single layer. I can do multiple layers. So here is X1. And then I have some layers here. And then another layer here. So that means this is the input layer. This is one set of neurons, and this is another set of neurons. And this guy will be getting the outputs of these units. If you do this, then the outcoming function will essentially be of the form of G of G of, right? Because if there is a G going on here, there's a G going on here. It's a nonlinear combination of two nonlinear compositions. All you will ever be learning in the neural networks is these weights, W1, W2, this one, all these weights. So the strength weights, the connection weights, and those weights will be the parameters. And it turns out, and this is the crazy part, that we know that a single layer neural network like this will learn all the lines. Any line that describes the data can be learned by this, because essentially it's a way of finding the best fit line. The question then is, how many layers do I need to learn other functions, non-linear functions? It turns out, and this is the crazy thing, that any given any continuous function, you guys remember continuity? Some of you? Given any continuous function, there exists some single hidden layer. By the way, this one is called the input layer. This one is called the output layer. And anything in between is called the hidden layers. So this is a network with single hidden layer, right? This is a network with single hidden layer. So given any continuous function, there exists some single hidden layer neural network that can approximate that function with arbitrary accuracy. So it's not like I need 2-layer network for quadratic polynomials, 3-layer network for cubic polynomials, 4-layer network for fourth-order polynomials. It's one layer, input, output, and no hidden layer. You'll only learn lines. If you just add one hidden layer in between, just one hidden layer, you can learn the universe of continuous functions. The only thing, of course, is I said there exists some hidden layer. The interesting thing is this hidden layer may well have nearly infinite number of neurons. I mean, unbounded number of neurons. You understand what I'm saying? So there could be input size, let's say 4, output size just 1 unit. The middle layer can have any number of neurons, 10,000 neurons. It's still called 3-layer network. It is called one hidden layer network. So then what else is left? Given any continuous function, there exists some single hidden layer network that approximates it. The next is given any function. That means even if it is discontinuous. Even if it is discontinuous, there exists a 2 hidden layer neural network that approximates it with arbitrary accuracy. At this point, you should be, if you still start off with me, then you should be asking, what the heck is deep in the deep learning? Do you understand what I'm saying? If I can learn any function with 2 layers, what am I getting by adding additional layers? Nothing expressiveness-wise. Nothing expressiveness-wise. Do you see what I'm saying? So don't think of, one thing I hope you will remember is it's not like, as I said, it's not like I need 3 layers so that I can get cubic polynomials. I need 5 layers so that I can get 5th order polynomials. No. With 1 hidden layer, you can get any continuous function. With 2 hidden layers, you can get any function. Done. The question, of course, is these are what are called existence proofs. Mathematics people basically say there exists a solution here. There exists some network. But the question, of course, is that network might be real fat in these hidden layers. Real fat in the sense it can have millions of neurons in the middle layers. What you might be getting by making the network deeper is each layer can have hopefully fewer number of neurons, fewer number of this, what we call neurons, are threshold units.
Okay.
Professor, I have a question.
Please do.
So what distinguishes a 1-layer function from a function that has, what distinguishes a 3-layer function from one that has 1 layer that's just 3 times bigger? Like, why is there multiple layers as opposed to just one massive one?
That's exact. We'll see this. By the way, this is all the preamble for the fun thing. I mean, there is going to be fun in the class. I mean, that we will be playing with the TensorFlow, with actually making networks in front of you that you can also play if you actually work with this. The difference basically is that the composition of the nonlinear. So basically what's happening here is these guys will be taking weighted inputs, which are then thresholded, and then that will become the output here, which will then be used by these weights, multiply those outputs by those weights, and then add them, and then re-threshold it with another G. Do you see what I'm saying? But a very interesting question that you asked, that's very close to what you're asking, and I will show that to you in a bit, actually is the following. What do you think is happening in these hidden units? What might be happening in these hidden units is that they are computing some sort of nonlinear expressions over the input values. Nonlinear expressions over the input values, which are then being linearly added by the last layer. So what might be possibly happening is, here is an idea. Suppose I have x1, x2, x3, x4. I'll actually no, x1, x2. In fact, just say x1, x2. Suppose I have x1, x2. We'll be seeing this in a minute, actually, in operation, that I might wind up having something which goes to two units, whose output then goes to the second layer. And in essence, what it is doing is this layer effectively might be computing something like x1 square. This layer might be computing something like x2 square, maybe. And then you add them up and you do the thresholding, and then you get this. If you don't like that, you could say x1, x2, and then I will expand the input myself up front by throwing in x1 square, x2 square, x1, x2 square root as additional features, because they can all be learned from, they can all be computed from the original x1 and x2, right? If you do this, then essentially you may be able to just combine them to a single layer and you will be able to learn. You will now be learning a line which is in terms of x1 squares and x2 squares. And I would argue that a line that is in terms of x1 square, x2 square is actually a quadratic function. Do you understand what I'm saying? So if I have y equal to mx plus c, I learned, except x is y equal to m x1 square plus c. So this is really a quadratic. I just learned it as a line because I threw in an x1 square in the beginning. All of this, believe me, will become clearer when we play with the TensorFlow thing in before. All of this is sort of dry discussion, but that will then show you some pictures that will make everything clear. Either that or the class will be over, and so you'll get what you get. But let's see what happens. Okay, but that's an interesting question actually. That the layers versus more more compositions of the input features themselves. Who asked? Shadmila is the one who asked. Okay, so if you hang around long enough, later on you will hear about something called kernel machines, and this is like total jargon being thrown at you right now, versus neural networks. That's the difference. One is kernel machines, one are neural networks, and they're actually equivalent. The question is, which is easier to learn? And I'll show you examples of that in a minute. Okay. The last thing before we go off is there are two kinds of, before we actually start the playground, is there are two kinds of learning that one may be interested in: regression and classification. The picture I've been showing you all this while, where there is data and I'm trying to fit a curve, that is typically called regression. Basically, I'm fitting a curve through the points that I've been shown so that I can then predict the values for the new points. This is called regression. How many of you have heard this word, by the way? Okay, this is regression. What is classification? A regression essentially is trying to predict y as f of x. What is classification? Classification is actually also, the difference is that here both y and x are both continuous. sometimes you might actually be having a scenario where what you want to do is not fit a single line, but say some points are good points, some points are bad points. So here is an example. All of these are good points. Maybe every point here corresponds to you, it's in some measure, let's say it turns out that there is X and Y coordinates, and your X-rays, for example, might be converted into just X and Y coordinates. Each X-ray becomes an XY coordinate. And I then figured out, based on your X-ray, whether or not you have COVID-related pneumonia. Let's bring it to 2020 fully, right? And then I found that all these points are essentially yes, COVID-related pneumonia. And all these guys are no. And given a new point, I need to figure out whether it's going to be COVID or not COVID. This is what you tend to think of as learning, but this is as much of a learning as this is. The difference between this and this is here, y is still again equal to f of x, but y is a discrete, categorical variable. And x, for here in this particular, x is x1, x2. I mean, so we'll call this x1 and x2. So I have points in the x1, x2 plane, and they have a label saying you are a positive for COVID, you are a negative for COVID. Based on that, given a new point, I'm trying to compute its label. Is it positive or negative for COVID? So then it is nothing but y equal to f of x1 and x2, except this function f essentially will basically give yes, no answers. That means it takes continuous variables and projects into discrete outputs. Do people understand what I just said? Okay, discrete outputs. Basically, it's still functions. It's just normally one way you can get discrete outputs over continuous variables, for example, is to use things like this: 1 by 1 plus e power minus x. This is called sigmoid function. Did I mention this in the class?
It was in the 3 brown, 1 blue, or whatever
Yeah.
videos.
This is a sigmoid function. What is a sigmoid function? What does it do? Let's look at it. Okay, when x is minus infinity, right? This will be e power minus of minus infinity. You guys know that e power plus infinity. So this whole denominator will be infinity. 1 by infinity is 0. Right? So somewhere along here, when you are farther down in this area, it will be close to 0. On the other hand, when x is plus infinity, this will be e power minus infinity, that is 0. Then 1 by 1, it will become 1. So on this side, it will be like this. And basically, the function kind of goes like this. That's sigmoid. So if you apply this function to a continuous quantity, then you basically push it into one side plus 1, 0 or 1. So you just converted a continuous quantity into a discrete quantity. Remember also that I think I mentioned, either I mentioned or if you saw in the 3 blue and 1 brown, the sigmoid function is the G function that is often used when you have a network which has, let's say, x1 and x2 coming, and w1 and w2 are weights, and then there's a function G here. The G is this sigmoid function. It's one of the threshold functions that people tend to use. Okay. So in this scenario, until here in the regression case, learning is about curve fitting. In classification case, learning is about drawing some curve such that on one side of the curve are all the pluses and the other side of the curve are all the minuses. Do you understand what I'm saying? Okay. And then the linearity would be if the data is linearly separable. In this particular case, there's a nice line that you can draw such that on one side of the line is all the positives, on the other side of the line is all the negatives. Then it would be called linearly separable. That is the case like finding lines in the regression. Okay. And so what would not be linearly separable? Well, there's a lot that can be done that in a minute we'll see. Like, for example, suppose I have data like this. And then these are all minuses. I'm also drawing. You see what I did just now? I made circular data. All the pluses are in this place. And outside of the circle are all the minuses. Is this data linearly separable? No. So that is like going for higher order polynomials in the regression. Are you with the play? Are you with the game until now? Now, let me change to TensorFlow playground and try to illustrate some of these things. Okay, what do I need to do? Okay. So first I need to go there, stop share. Okay, start sharing. Then there, go there. Okay. And I'm going to go start sharing. Where am I? Just give me a second. I'm trying to find out in my desktop too. Oh yeah, this. Okay. Do you guys see what I'm saying, which is tinker with a neural network right here in your browser? Do you guys see it? I no longer can see your faces. Oh, no, I can see your faces too. Maybe
Yes.
not. Let me see. Okay, 1 second. Where are you guys? I need to figure out. Okay, so at this point, I unfortunately, let's see.
Yeah, your screen is visible.
It's visible, right? Okay. Unfortunately, oh, okay. Now I just need to make sure that I have one thing. Okay. Now I need to see your faces to see how lost you are. Otherwise, it's hard to figure out. Okay, fine. Okay. You can still see my screen?
No, now it's like just a
There was
sliver.
something funny, right? Huh. I don't understand. Your screen is being paused. The screen share. Okay. Stop share. And let me try it again. Start sharing. Okay. Now it works, right?
Yes.
Okay, let's play. Let's play. Okay. So this thing is, you can play with this at home. I mean, I'm recording this, so you'll see this, so you can play with this at home too. And this is sort of like a playground for everything that I showed you. So you notice on this side already, they gave me some circular data. So the blues are, let's say, positives, the oranges are negatives, and I need to separate them. Okay, so let me start simple. Let me start simple and consider just this. These are simple data, and then I can change the number of hidden layers, 0 hidden layers, okay? And I have no hidden layers, and it just basically the inputs x1, x2, and outputs. Okay, what we are trying to do is each of these have some weights. Right now it's set to some random weights, because of which there is a current line is this, and this side is blue, this side is orange, according to this line. Is this line correctly predicting the blues and oranges? No, right? Because there are blues, there are oranges on the blue side, there are blues on the orange side. Every time that happens, that's an error. And you add up the number of errors, that would be the loss. In fact, what you would do is you will take the prediction of the line, whatever the network is saying is the class, and the true class minus that, square that, sum all these errors, and that is called the loss. The loss is the training error, essentially. And what I'm trying to do now is the moment I actually just say play here, it will try to quickly try various combinations of the weights, W1 and W2 here. In particular, what it'll do is it'll just do the simple calculus. It'll just try to figure out the best way to modify the weight by gradient descent until the error becomes 0. And what you will see is the reason I'm taking this time, this long to explain is the moment I click this, over. We learned. Right away. I made a huge deal because the moment I click it, it's over. Okay, what happened there is essentially, and you notice the epochs. Epochs is the number of times the weights are being changed. What does it mean to say weights are changing? I'm doing this gradient descent. I take the initial weight, I subtract from this the alpha times the gradient in that place. And I'll get the new weight. And I keep doing this until essentially I find the minimum. The minimum in the error space. Basically, we are looking at the function, which is the error function. And I'm trying to find W1 and W2 such that the error is minimized. That's the gradient descent that's happening here. Okay. Right. So, and you'll notice what it happens. One other thing that happens is if I reset it, one other thing that happens is if you look here, it is telling you currently the way it currently is, the test loss is 0.180, the training loss is 0.165. There is a test points that it kept without showing you, and it's checking whether or not you are correct on them. Okay, and the training loss you can actually see yourself. In this particular case, the training loss would be dependent on whether there are blue things in the green and orange region and vice versa. And when we start stepping, you notice how the line just keeps changing. Right? In fact, let me do this again. So now I have a line like this. If I step through this, if you click this, it'll be stepping through. You'll essentially see the line just changed. When a line changes, you're just changing mx plus c, m and c, that's all. The m and c are in terms of W1 and W2. And as the line changes, you are computing the error. And you notice that both the training error and test error have essentially become 0. You can't see two curves because there's only, training error as well as test error have become 0. This particular single layer networks are called, there is a great name for them. Let's see if I can write here. I should be able to write. Yeah, good. Perceptrons. perceptrons. And a guy called Frank Rosenblatt basically came up with them in 1962. I must have mentioned it around the time I was born. That was the big deal. He was so happy that anything can be learned by his perceptron machine. And it was essentially doing this kind of weight change until you find a line separation. Except Frank himself did not understand what you already understand. That's the funny thing about civilization, right? A PhD professor in Kernel didn't understand in 1962 what you understand as first-year students because of the discussion that I just had. Mostly because I wasn't there to explain to him, but mostly also because human knowledge has improved, right? So he didn't quite realize that what he was doing is essentially learning this function that is separating the positives from negatives, and that if you only have a single layer, you can only learn lines. You can only learn lines. That means only linearly separable concepts. Only linearly separable concepts. He didn't know this. And so a guy called Marvin Minsky, who is one of the people who started the field of artificial intelligence, Minsky and Papert, basically realized this. So all of research is somebody else hasn't figured out, somebody else did something and you figured out that they are wrong. So you get to say nya, nya, nya to them. That's all research is. Because when you get to say nya, 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 then you are improving human knowledge. Okay, so what they basically said is, okay, man, so if you are able to do this, why will you be able to learn everything? So for example, suppose I have this data. Do you guys see what is happening here? It's like the orange is in the 2 quadrants and the blue is in the 2 other quadrants. Will there be a line that cleanly separates all the blues from the oranges? A line? No way. Right? So they basically said, look, things like this. In fact, there's a more interesting way. They actually looked at just Boolean functions. I won't want to get into that. But if you take this example, and if you try to run this here, let's see what happens. Did the error training loss go to 0? It's 0.5, still darn high. Because essentially, the best you're able to do is you're saying this whole thing is blue, this whole thing is orange. So half of the blues and half of the oranges for errors, according to you. You see what I just said? Right? And so if I restart this and step through, for example, it will try, it basically tries random things and it's just unable to figure out. It doesn't, the best function it gets is going to be a line, and a line cannot separate this concept. So the idea of linear separability is something that they figured out, and they made na 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 to Frank Rosenblatt, who got depressed, dropped out, and people stopped doing this stuff for quite a long time. Okay, and then what all we care about really is, hey, there are these hidden layers business. Let's try adding a couple of hidden layers. Right? If I add a couple of hidden layers, then I restart, what happened? You see what happened? It nicely found, it's not a single line, it basically found almost like a pair of lines that just sort of get close to the blues. If I add some more, you guys impressed? Now we essentially figured out how to separate them. Now, one other thing that you have to remember is the moment I added a hidden layer, every function that at all can be learned with one hidden layer. The only question is how many units are supposed to be in that hidden layer. With 2, I did okay. The best with the 2 was that. With 3, I get something like this. It's still okay, nothing great. With 4, look at that. By the way, here's the other very interesting thing. Every time, I mean, do you notice that movement? That's basically, this is gradient descent. It's trying to find the best optimum, and it's actually sort of oscillating. It's beautiful. You may not ever again see this, unless you play and you just happen to, because remember, many of these things are starting in the function at some point and starting making gradient descent. Depending on the place where you start, you can get into different regions. In fact, the last time I had the same version, actually, in fact, this is very interesting. In fact, what I showed here is 3 neurons in the middle layer and 2 neurons in the last layer. And that's what was happening here. So whereas if I just make it 4 neurons here, okay, if I keep increasing the number of neurons, I'm sorry, I'm doing layers instead of neurons. So this is the number of layers and this is the number of neurons. If I keep increasing these, in essence, it's not going to change. It just takes longer to get to, notice that because there are many more, it's taking much longer to converge. It's taking much longer to converge because it needs to learn a lot more numbers. Okay, it will be able to converge because if it can converge for 4 neurons, it will converge for 8 neurons. Let's just stop this and restart. It will slowly, if you wait long enough, right now it's still not good, but eventually it will get the other part of the blue too. Whereas in fact, if you just reduce the number of neurons in the middle, it's learning faster. It almost, you have to be able to understand both of these at the same time. Okay, one is, I said, if you increase the number of neurons in the middle layer, it's as if I'm allowing bigger and bigger polynomials. So that means I have even bigger hypothesis space. So I should be able to find the best hypothesis in that, which is no worse than the one in this smaller space. But because there are so many more hypotheses, it's a much higher dimensional function that you're trying to optimize. It takes longer. Which I wish I could show you something. Maybe I'll show you a little later. Let me, I'll see if I can show you that. Yeah, so oftentimes, even though these, for simple examples, it gets over, most of the time, if you have many, many parameters, it takes forever for the network to learn those parameters. That means get those parameters, those weight parameters, to a point where the error is sort of minimized to be at least in a local minimum in the space of the, in that function. So oftentimes, basically, as I said, when I said AlphaGo or something would have taken 1700 years to train on your machine, while it took only 5 weeks in DeepMind's machines. It is this number of epochs that can be done in doing this weight change. Each weight change is a little thing, but it takes a long time to do all of them. And the more the parameters, the longer it takes. Okay? Any questions? on this. The other thing I can do then is I'll say, I don't like hidden layers. I don't like hidden layers. So why can't I remove? Oh, no, okay, no hidden layers. I don't have any hidden layers now, right? If I don't have any hidden layers, then it's like normal, like this. Can I learn this without any hidden layers? We now know how you can learn it with hidden layers. Can I learn it without hidden layers? That is the answer to where's that girl who asked me the question earlier? Who asked, what's the difference between layers versus inputs? At least I was talking about Sharmila. Okay, Sharmila, look at this now. This, if I try to learn, it's not going to go anywhere, right? Because it's basically not going to be, it will still have very high error. But imagine I threw not just x1, x2, but x1 square, x2 square, x1, x2, sine x1, sine x2. If I know x1, x2, you have a calculator, you can compute these other numbers, right? It doesn't require artificial intelligence to compute x1 square. Now, if I do training, I'm done. Magic. We went from needing a hidden layer to not needing a hidden layer. And what's weirder is if you look at these things actually tell you the weights of the connections, the strengths of the connections. And you notice that the strengths of all the connections are very close to 0, except this fatso, which is x1, x2. And what the machine basically figured out is just look at x1 times x2. If x1 times x2 is positive, it is blue. If it is negative, it is orange. Right? Because the blue is in the first and third quadrant, where x1 times x2 will be positive. And the oranges are in the second and fourth quadrants, where x1 times x2 will be negative. Do you see what I'm just saying? So you could learn this function either by increasing the input, by basically taking the input, blowing it up, compute all sorts of arbitrary functions of this input, make that also as part of the input, and then try to see if I can find a line. But finding a line in this bigger input space is actually finding a polynomial in the smaller input space. Do people understand that? Because this is just a linear function on a nonlinear input, x1, x2. If you guys understand this, the difference between these two approaches, the first approach that I showed you with the hidden layers, that's your neural networks. This approach is kernels. What kernel machines do is they take the input, blow it up into infinite number of dimensions, and then find a line in that infinite dimensions, and then come back into the original coordinate space. In essence. And both of them can do what you're trying to do. And right now, as we speak, like next Monday onwards, NeurIPS conference is starting. It's one of the main AI conferences. In fact, those are the guys who are crazy about neural networks. There are tons of papers still trying to understand when is kernel machines reasonable versus when is neural networks reasonable. And you understood this already here. Okay. In some sense, what was happening when you did this x1, x2 thing here is if I were to remove them, right? And if I were to put a couple of hidden layers, I'm sorry. And if I were to train, it did find this, right? So in essence, it is computing some functions of x1, x2 in these 4 units. which then it is composing linearly in the last layer. So this is why people say that these hidden layers are called features. Somehow the machine figured out what features to use. It's some kind of a function over inputs. And then they are linearly combined in the last layer. That's why if you either can let it do this here, or you can remove them and just increase the number of features upfront itself, and then just do it and learn. Okay. Okay. Now, by the way, this stuff, some couple of you were crazy enough to say in the thing, in the write-up that, we really wanted to learn a little more technical stuff. This is technical stuff. This is basically stuff that you won't understand in most Intro to AI courses still. Okay. And by the way, I should mention that there is a Intro to AI 471 link I will put up too that I have taught. If you've gotten anyway used to my annoying voice, there are videos of that entire course. You can watch them. That's the best way to spend Christmas time. And then you would have done not only the first one credit invitation to AI, but you have completed the introduction to AI by time January comes. Okay. And then you would have enough of whatever it is that you wanted to learn, that you wish more technical stuff, that you get that. Okay, the last thing I want to do when I have this picture is I want to try with some other data. So the circular data. Okay, the circular data clearly, again, for the circular data too, if I remove this, with just single layer, I won't be able to learn. I mean, no hidden layer, I won't be able to learn. The best I can do essentially is still 0.5 loss. The loss can highest be 1 because they're normalizing the error. Okay. If I start putting in hidden layer, just one hidden layer, and put more units there, and then train, that's it. All it did is it actually figured out some approximation to a circle. It found in this particular case a nice, cute little hexagon. No, it's actually a pentagon. It found a nice little pentagon. It's not linearly separable, but it is 5 linearly separable. You put 5 lines, you'll get a polygon, and the polygon nicely keeps the blue guys happy, and the red guys can be outside. I'm not getting into politics. I'm just talking about positive, negative examples. Okay? You see what I'm saying? So all you needed is just one hidden layer. The other interesting question, of course, is what exactly is happening when I have more hidden layers? Let's do that too. Put a whole bunch of layers. And in this case, just remove the number of things. Let's say something like this. And I don't know whether it will work or not. I just made this architecture, right? And then I'm going to see what's the best I can do with this architecture. You see what happened? I don't know if you should be looking at this guy. When we started, it was strange. When it started, I don't know if it will again happen or not. Every time you rerun it, it's a random thing, right? Because it starts from some point in the function and does gradient descent. Okay, so let's do it again. And then look at this output, which shows both the training error and the test error. Look at how things changed and went up, and it's kind of still trying. And last time it actually, by this time it converged. It's taking longer this time. It's essentially, again, this is the other part. Depending on where you start on the function, it might take longer or lesser time to find the minimum. This time it actually didn't do all that well. But you just saw, I mean, I even recorded it. Last time with the same damn neural network, it found a nice little pentagon. You see what I'm saying? So the question then is essentially in trying to figure this out, one of the questions you have to ask is, what should be the architecture of the network for which I am trying to find weights? And you can always say, why the heck, why not I just increase the number of layers and increase inside every layer I put your thing. That looks good. This is a nice sledgehammer to break an egg. Because remember, a bigger network will always contain the smaller network inside it. Just like lines are in quadratics. And lines are, if you go up to second order polynomials, that is a superset of just first order polynomials. If you go up to seventh order polynomials, that is a superset of all the polynomials up to seventh order. So anything you can do in the lower, you can do in the upper. Except the space is much larger. So what happens in this kind of a case, is it takes much longer, potentially, although famous last words, right? I mean, obviously it's not listening to me, but this is the kind of thing that gives people the wrong idea. Now you will remember, screw what Rav said, whatever my data is, I will use 850 layers and 800 neurons for each layer. Because I tried to convince you that it will take longer, and with my luck, it just went very fast. Do we know when this happens? No. Do you understand what I'm saying? It's like a weird scenario that finding the local optimum in a much larger space is, at least in this one instance, wound up being faster than finding the local optimum in the subset of that same space. Mind-blowing. We don't yet know why that happens. But people know that this kind of a thing happens, because of which they try to start with the biggest network money can buy. Okay, there are people out there who are learning a quadratic function with 15 layers and 17 units per layer. Okay, let's just try this once more and see what happens. I mean, with my luck, you guys just lucked out. This is strange. Like, I'm resetting it. Look at this, how many net weights are here? And they're all randomly initialized, right? And then I'm restarting. So obviously you will never believe anything I said. You're going to say, get the bigger function. I mean, that is basically, the higher the capacity, the faster you might be learning. Even though it's supposed to take longer, it's actually becoming faster. That leads to the next mind-blowing question, which is whatever happened to our happy bias variance trade-off? Remember, I told you that the test error should become worse if you unnecessarily increase the capacity of the network, increase the capacity of the polynomial. You agreed with me. You agreed that, learning all the kinks in the data will be good compression, but bad, good compression, but bad learning. And yet, with my luck and your luck, I just showed that the more complex the function, the faster you're learning. And furthermore, it's not learning in the sense that the training loss actually is zero, and test loss is also zero. Test error is not worsening either. How are juniors ever going to learn that it's not good to break eggs with the sledgehammer? They'll just buy a sledgehammer when they're kids and then start working everything with that. That's exactly what's going on right now. How many of you at least feel the frustration I'm feeling right now, that I have this nice little theory here and that theory went out the window. 15 minutes back, we had a theory, and now that theory went out the window. For you, it's only 15 minutes back. For statistics community, it's been last several decades, they've been saying this is the reality. You try bigger capacity functions, you will rule the day. And then deep learning folks are basically saying, nah, look what's happening. It actually becomes hard to figure out why the bias variance trade-off is not holding in neural networks. The answer is we only now have, right now, we only have provisional answer. And the provisional answer, let me actually, you guys had enough of this stuff? I'm going to get out of this right now. Okay, actually, let me show one more thing, which is, this is circular data, right? I'm going to just remove, remember this, we do want to come back to this before we leave. Anyway, your semester is over, so I don't feel particularly bad. But before we come back to this, I want to actually remove all the hidden layers. Now it's just normal. I want to show I can learn this with kernels too, right? So I throw in x1 square, x2 square, x1, x2, and maybe sin x1, maybe sin x2, and then I train. Got it. That's the kernel solution. Okay. At this point, you'll be asking, what am I learning? You could learn the same damn thing, quote unquote, with a smaller network, bigger network, humongous network, and just zero hidden layer network with just more inputs, with just more functions of the inputs. And furthermore, when I showed you that bigger network, all those internal nodes, each of them are computing some random nonlinear function of the inputs, x1s and x2s. You don't know what they are. The machine just figured them out in trying to minimize the overall error function. And you don't know what those things are, because of which you don't actually know whether the system is looking at the world the same way you are looking. Okay. Now I'm going to get out of this and I go back to my, where am I? Stop share. Okay. And I'm going to go back to my other screen. Okay, so you guys can see it now. This slide was there first class. I didn't want to go into it, but it's kind of tells you where we are in this part of AI, in this part of learning from data. Okay, many unintuitive aspects of quote unquote deep learning is we basically right now we say it works. We don't completely understand why anything works. Okay, state-of-the-art networks might have more parameters than data. More parameters means more weights than data. So imagine I give you let's say 4 points. And you'll say, yeah, let me take a 39th order polynomial and fit it through these 4 points. This is anti-compression, right? Because you only had 4 points. Now you had nicely converted into 39 parameters. right? Because a 39th order polynomial will require 39 coefficients. That's what you'll wind up learning. Okay. And so remember GPT system, GPT that we talked about, the GPT-2 system has 1.5 billion network weights. That means every one of those edges has a weight. There are 1.5 billion weights. That was already old news. The GPT-3 has trillion total. I think, sorry, it's 17 billion, I think, if I remember correctly. Okay, so it has 1.5 billion network weights, and it is trained on basically 8 million web pages. So in some weird sense, there are only 8 million web pages. You could say that if you increase the number of weights, then at some point of time, the network can just memorize the data. Do you understand what I'm saying? Remember this connection we made between compression and learning, right? Basically, if you're starting with such a powerful function, a function which has such high capacity, then in essence, you can learn all the points and memorize them. And we made this point that memorization is not learning. Memorization, basically, unless exam asks the same questions that I asked during the class, memorization is not the way to do well in the exams. You need to understand the pattern. And yet, they sort of seem to work. Okay, and this should be a recipe for overfitting. If there is anything like overfitting, this is where it should be, right? Because essentially, I am taking the training data way beyond the point where it became zero. I'm increasing the complexity of the hypothesis way beyond the point where the total error became zero. And normally that's where we said it is supposed to start overfitting. But supposedly it's not. Do we have a theory? It turns out about a year back, and this is how close you are to now the state of the art, and nobody really knows even if this is going to hold next year. They came up with, you think of this as essentially, there is this idea now that this is what happens. This is what is called double descent. That the original fun thing that we had about bias variance trade-off doesn't seem to work, because you just saw me try to make it happen and it didn't happen in front of you. That's pretty embarrassing. And so I come up with a new theory. The new theory is that this is what happens, a double descent phenomenon. I'm bringing this up only to make you realize how close, how some of it is very easy, some of it nobody actually understands why it is doing what it's doing. And when we are saying it is not overfitting, how do we know it's not overfitting? Maybe you thought that the system learned the school bus and the dog quite well, and you added some amount of noise. It got these, and you thought they still look like school bus and ostrich. I'm so sorry, school bus and dog. But the system now says this one is an ostrich and this one is also an ostrich. Are you surprised? Maybe we shouldn't be, because we don't understand failure modes yet. And now people are saying, I'm going to be able to take your X-ray and tell you what disease you have. And you should ask yourself, do you want to do that, or do you want to think twice? It's at once amazing that we came this far. It's also the case that there's stuff that we don't understand. And this is technology that's being used right now. And this is all connected to the bias part. It's also connected to this adversarial examples part, which we talked about, etc. Okay. So, two other things. I am going to take two more. I want to make two more points before you go off. Okay, this stuff is basically conceptually, if you understand this, you understand a whole lot more than most people do about how neural network learning works. But I understand that there's this, cartoon that, what we tell the dogs and what dogs understand. We speak, fluently to our dogs, and the dogs probably kind of understand their name and nothing else. I realize that I'm like hanging around in this field for 35 years, and you guys just by mistake showed up in this class, and some of you by mistake said, why not more technical? And you got, stuck with this. So I don't quite know how much any of you understood, but it may well be that 4 years from now, when you're doing actual intro to AI, or maybe 2 years from now, then say, oh, that's what Rao was saying. And if that happens, that's good enough. Okay. Two other things I just wanted to mention. I don't know why, but it's not that we are not already delayed, but it's the last class, and why do I care? And you have nothing else to do. So I don't have to at all feel bad. You have no exams. Even the one girl who had an exam showed up now. So Emily, you are stuck. Okay. So two things which we mentioned in the class, I just want to bring up. One is infinite horizon rewards. Remember we talked about, that this stuff, these kinds of guys, right? And then the agent goes through this and collects the rewards. And the best policy is the one that is supposed to sort of maximize its expected cumulative reward. The problem is if the agent lives infinitely long, then it can essentially do infinite number of state transitions. Every state transition, it gets a small reward. You add all those infinite small rewards, you get an infinity. So if you live infinitely long, it looks as if all policies would look equally good to you, because every one of them will have an expected cumulative reward of infinity. You understand what I'm just saying? How do we deal with that? If we don't deal with that, then in essence, when we have what we will call infinite horizon MDPs, which basically are indefinite horizon and infinite horizon MDPs, then keep again. I'm going to add a couple more slides here. If you get infinite number of rewards, how can you separate good from bad policies? This is not a theoretical question. Imagine your semesters are infinitely long, as for example, today's class is, right? You screwed up in the first 18,000 exams. Does this matter? No, there are still infinitely more exams that you can still work on. So it looks like every policy is as good as every other policy. In the sense, not showing up for the class infinite number of days will still be fine, because you can come up with the other infinite number of days. You know the whole, puzzles of infinity, right? The Hilbert's Hotel. Hilbert Hotel has infinite number of rooms, and one day it got full, and infinite more people came up, and we need to put them in. What do? Well, Hilbert says everybody goes to the room that is double their room number. So if you are room 1, you go to room 2. If you're in room 2, you go to room 4. You go into room 4, you go into room 8, and so on. Then there are infinite number of empty rooms. You put this new infinite number of people inside these empty rooms. So then Hilbert continues to be a good hotel manager. By the way, why do you guys think I said Hilbert? Hilbert is one of the greatest mathematicians, and he actually also talked about like 10 open problems in math back in like the turn of the century, and and he's considered smart enough that he kind of knew what are important problems to be solved, etc. But anyway, that's all over. So the question then is, I have R0 plus R1 plus R2 plus R3 plus R4 plus blah, 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 R infinity.
You could take like the average for every step or something.
Who said that? Okay, so one great idea is look at average. That means don't look at policies in terms of their total expected cumulative reward, but differentiate policies in terms of their average expected reward per step. So you might be saying, infinite number of days getting zeros on the exams is too depressing. So essentially, I will look for a policy which will give me some amount of marks in the beginning too. Okay, that's basically called MDPs. That idea is called maximizing average gain. Maximizing average gain. Emily is onto something, because this, by the way, is what your stockbrokers. How many of you have stockbrokers? I always ask because there may be a student who is a stockbroker and I can be friends with them and they will put me in their will when they make a lot of money, but none of you do. But stockbrokers basically, the stock managers, what are they supposed to do? They're supposed to maximize the amount of money you have by the time you probably die, probably. But that's not what they actually do. They try to maximize the gain per year. So this year they will maximize the gain. And by kind of doing arbitrarily bad investments, which are high risk, and they will get all the commission, at which point they'll skip town because they get their bonuses based on this year's reward, and they'll skip town. Next year, the stock market collapses, your money goes off, but government will come in and rescue the big corporations. That is basically average gain maximization. There exist MDPs like that. That's a very reasonable thing. But imagine you don't want to do that. You don't want to be such a sort of a antisocial person. Can you still make an infinite sum of real numbers be finite? One plus half plus 2 cube, 2 square plus 2 cube plus 2 power 4, 2 power n, limit n tends to infinity. What is this?
2.
What?
2.
2. You guys realize this, right? This is an infinite series which sums to 2. How do you know this? Because the gamma, which is the common ratio, is half. And if you have an infinite series with a common ratio half, then the sum is 1 by 1 minus gamma, which is 1 by 1 by 2, which is 2. If you don't believe me, you have calculators. You can keep on adding this stuff until cows come home, or you die, and then you'll see that it's becoming closer and 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 closer to 2. It'll never be exactly equal to 2, but it'll be closer and closer to 2. In limit, when you take infinite number of these numbers, it'll become 2. What has this got to do with my problem? What I would say is, suppose you have this issue that your problem is R1 plus R2 blah, blah, Rn, where limit n tends to infinity. This is your reward, and this can be infinite. I will basically consider the max, let R max be the maximum reward you get in any state. Indulge me. Maximum reward you can get in any state. Okay, then I would do the following: 1 by R max. So no, not that way. Sorry. R max, you can just do it. R max plus 1 plus gamma square plus gamma cube, blah, blah, blah. In fact, what I'm actually trying to say in a better way, maybe, I don't know if I can do this. Sorry. This, you want to make this sum be finite. I can, sorry, just give me a second. To make this sum finite, I will just say, I will take a gamma such that 0 strictly less than gamma, 0 less than or equal to gamma strictly less than 1. It's a real number between 0 and 1. And I'll say gamma power 0, R1, gamma power 1, R2, gamma power 2, the next R3, etc., gamma power n, Rn. If I do this, you can convince yourself that this will be a finite sum, because I can always take R max, which is the largest reward of anything out, then everything will still be less than 1. And so the actual sum would be less than R max times 1 plus gamma plus blah, blah, blah. And so it will be less than R max by 1 minus gamma. Crazy nonsense at the end of a Friday. The question is, do you think you do this in life? I can give you $10 right now, or $100 K years from now. Is it equal for you? Where depending on the K, you might start saying, I would rather take the $10 now than wait for 100 for, let's say, some of you might say $10 now. And if I say, I'll give you $10 now or $100 tomorrow, some of you might say, screw it. I may or may not be here tomorrow. I'll take 10 right now. Okay. And if I say $10 now, or and some other people might say, oh, no, we'll take $100 because we are doing nothing today. It's not like we're going to be in a car accident or anything. So tomorrow I will get $100. So I'll take the $100. That's kind of looks like a better deal for me. But even those of them, I would say $10 today or $100 10 years from now. They'll say, that doesn't make any sense. 10 years from now, who knows what I'm going to do? We don't know whether US currency will have any value left 10 years from now. What is the point in saying $100 10 years from now? When you did this, you are essentially comparing $10 now to gamma power n $100, where gamma is the discount factor, where n instead of n, let's say k. Gamma power k times 100. Where k increases, this gamma power k becomes close to 0. So 10 looks better than gamma power k times 100. This is called discounting rewards, discounting future rewards. We started this as a mathematical trick, just so that infinite sum of rewards will become finite. But I will argue that it actually is very close to what people do. they always discount future to now. There would be very few people. Suppose I would say $10 today or $1 10 years from now. Do you think there would be anyone in the world who would take that, the $1 10 years from now deal? You don't expect anybody like that, right? In general, you are saying the future rewards to be commensurate with the current reward, they should be bigger because you're going to discount them in terms of how long you have to wait for them. And the way I'm discounting it is I'm multiplying it by gamma power k, where k is the amount of time I'm waiting, and gamma is the discount factor. The question then is, what is the difference between people who have small discount versus large discount factors? And probably those of you who actually saw that, last lecture thing may already understand this, that you can imagine that my thing is that if you are, let's say, in the middle of a, let's say, I think what's on the, some battlefield, okay, where there may not be any tomorrow. You are better off having gamma to be extremely small. You might want to have gamma to be 0 because immediate reward is the only reward that you'll ever get. All this nonsense that I told you about value is what you should be optimizing for, and value is not reward, value is not even proportional to reward. Tell that to a little kid who is in the middle of a battlefield that he didn't create, or he or she didn't create. They're going to say, just give me what you can right now, because I have no idea whether I'll be around 1 hour from now. So they will have very low discount factors. On the other hand, if you're in a stable society, if you think the world will exist just like the way it is right now, you are likely to have a higher discount factor. So my joke is graduate students essentially have high discount factors because they assume that after they complete the elementary school, the junior high, the high school, the bachelor's, the master's, and the graduate school, there still will be a country which will offer them a job. On the other hand, some kids might be thinking, this entire country looks very shaky. I've already completed an elementary school. Let me start exploiting my money. And those guys have extremely low discount factors. So the thing that I want to mention is that you always discount future reward with respect to current, and it has very interesting connections to real life. You will do this all the time. If I ever always tell you, like, would you rather have like an A+ grade in this, or maybe, sorry, what's A+? I should say A+. Would you rather have a B- grade in this course, or like an A++ grade when you take your first PhD course with me? Right? You might say, give me the B- right now, please. And that's not because PhD A++ is not great. It's just that you don't know whether you'll be around, whether or not you're actually going to do that. So you would rather just take the reward right now. When you did that, you made your gamma to be extremely small. You really should have taken the PhD A++. You understand what I'm saying? The last point I want to make, keep this. Last point I want to make, because we brought this up once, and I'll only just make it short, and then we'll go off to the ending, blah, 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 is, remember we talked about what is value versus money. Somehow we tend to associate money with value. Okay. It turns out, and in fact, if you associate money with value, then it actually turns out that many things like lotteries, as I said, lotteries can be really seen as a tax on stupidity, because lotteries don't make any sense if you actually think money is equal to utility. But the point is, value and utility is another name. which is even a better version is happiness. And you say happiness, but technically we say utility or value. The question is, you're sort of assuming that when you make your normal arguments, you're assuming that this is happiness, this is money. You're assuming y equal to x line. If you have $10, you are 10 happy. If you have $100, you are 100 happy. If you have $1,000, you are 1,000 happy. If you have minus $10, you are minus 10 happy, which means you're kind of sad, 10 sad. Do you see what I'm saying? In that way, if in fact you look at the world this way, then indeed it is the case that lottery is a tax on stupidity. But really, money is not exactly converted to utility in this linear y equal to x fashion. If you ask people, essentially, how much is money worth to them in terms of utility? And so the utility is in the y-axis and the money is in the x-axis. The kind of curves you get are more like this. In fact, if you do a bigger curve, you get this nice S curve. Remember this, because it explains lots and lots of things that happen in life. For you, $10 is a big deal. For Jeff Bezos, another million, no big deal. Because he's already at this level of utility, and another million will be at that level of utility. It's basically the same. But where you are, a million extra would be that much increase in utility. In fact, I can make you happy with just $10, especially because none of you have stockbrokers. And the negative side is also important. Okay, when you buy a lottery ticket, you are losing $1. So there is a negative happiness. But then you are expecting that because you are the chosen one that gods have chosen, you will be making the $1 million. You will be the next Bezos. And you throw in the probabilities, you will still say it's a good deal. If on the other hand, if you see Bezos buying lottery ticket, tell him it's a tax on your stupidity because you are here. What the heck are you trying to do buying lottery tickets? So it's important to differentiate between money and utility. And these curves can be different for different people. We had this long discussion at one point of time as to what are you trying to optimize. Typically, people try to optimize happiness. And they just don't know how the happiness is connected necessarily to the money. But most people's money to happiness curves look like this. And it's worthwhile keeping that in mind. And then this is what you're trying to optimize with respect to your decisions. Okay. So that's all I wanted to say. A couple of things that before we end are you guys wrote your summaries. The reflections, course reflections, and we, as I said in the beginning of the class, we processed them. I think only some of you did not, for some reason, submit their reflections. You better do, because that's important. It's part of the class. I think I had 18 people submit, and those are the ones that we kind of did a word cloud. And so this is the first question, which I believe, I forget actually, what are all the questions? Do you guys remember? You guys don't remember? You reflected on this stuff. My God. Okay. Let me just see 1 second.
I believe it was 5 topics or ideas we appreciate.
Okay, I will tell you what the questions are. Yeah. Okay. Yeah. Okay, so the first question is list 5 or more ideas about AI that you appreciated over the course of this semester and explain why they appealed to you. That was the first question. And the word cloud of this has this. So I guess deep fakes, explicit versus tacit knowledge, deep learning, presumably. Many people thought about biases. People also talked about neural networks. You guys have seen word clouds, right? So the bigger the word, that means more of you have said that, essentially. Okay. Some people also said Turing. In the small case, I don't know what people said. Yeah, I think threats. Maybe some of you are talking about threats from AI, presumably. Some people actually talked about augmentation. That means replacing humans versus helping them, augmentation. Actually, I should have done this other thing too. But anyway, so now people talked about knowledge. Of course, everybody talked about intelligence. And the interesting is very small. I really expected it to be much bigger, but it is there. Okay. So that's at a very high level. That's what people said. I read all of them. I tell you that you should, read everybody else's, because maybe other people got more out of this or less out of this than you did. And it might be interesting to see. That's about the first question. The second one was list 3 or more non-trivial technical details of the algorithms and the relations between the ideas you understood. So people talked about Polanyi's paradox. People talked about gradient descent, of course, gradient and descent nicely. People talked about causality versus causal versus correlation. Okay. And people also talked about, of course, learning. They also talked about humans, I guess, presumably. Weights, presumably weights of neural networks. And then what else? Yeah, correlation versus causation. That's pretty nice. You have the causality and correlation. You talked about environment. It's very important. So let's last quiz. The environment that you live in your day-to-day, is it deterministic or stochastic?
Stochastic.
Okay. Is anybody living in a deterministic environment? You can sometimes change your environment such that it will become more deterministic. If you have kids, make sure that those kids live in a more deterministic environment, right? We can stabilize our environment. Is the environment that you're living in, is it static or dynamic?
Dynamic.
In general, it is dynamic, but you want to get a good night's sleep, it better be static. Right? You are the only agent, you are happily sleeping. Okay, static versus dynamic. Fully observable, partially observable. The real life, is it fully or partially observable?
Partial.
Partially observable. Okay. So those are things that people talked about. That's kind of important. It's very useful. And in fact, any of these other ones make the problem harder to handle. Okay. That's one. And the third was list 2 or more ideas that transcend AI that got discussed anyway, that made an impression on you. These can be anecdotes, factoids, philosophical issues, blah, blah, blah. I guess, again, these questions become less and less amount of writing. And so the word clouds don't have enough frequencies of the words. So let's see. Some people apparently talked about cybersecurity. I'm not quite sure where anybody talked about diplomatic, ethical things, presumably. I don't know, not too much makes sense at the word cloud level here, presumably, because the data is sparse here. Sorry. Okay. No, sorry. Actually, yeah, I think I missed one in between. That's the problem. This one, yeah, I think what happened was this one is the question for, wait, give me a second. I think I missed putting some of them. Okay, give me a second. I'm going to try and go to my, okay, there you go. Yeah, no wonder. Can you see what I'm showing here? Okay. Yeah, okay. There you go. Now I kind of messed up. So this is part one, okay, that you saw. And I'm sorry, this is part one. And this is part two, which is list 3 or more ideas that we talked about, Polanyi's paradox, etc. And this, okay. And then this is part 3. Okay, that makes a lot more sense. Part 3 is list 2 or more ideas that transcend AI. So you talked about bias, you talked about society, you talked about adversarial examples, presumably. For some reason, people liked Samsung, I guess the Blink example. And then 3 blue, 1 brown. Of course, they said transcended multiple times because we're talking about transcended. And then what else did you say? Mirror. So several of you basically like the fact that AI tends to mirror the society because it's learning the data from the society. So that's something that came up. Okay. And then the part 4 is this. Okay. So part 4 was list 1 or more idea topic that you wished we discussed in the class. And I guess those are the ones where some people basically said they wanted, I guess, let's see, I mean, this workplace was that. So some people wanted to see how AI would be used in workplace. Some people wanted to talk about cybersecurity and AI. So these are the things that people were missing that were not done in the class. That's why it is a sparse map. And then the last one is, in a few words, how would you contrast your view of AI before and after taking? And again, it would be a reasonably okay thing. So it's intrigued, ethical, I don't know what. It confirmed for some people, kind of, they understood. For some people, they said it broadened their view, etc. But I mean, this is just to give you a sense. I think actually I read all the ones that have been posted. I made comments, and that sort of tells me who actually got what. It's surprising, you know, as they say, as I said, mouth is the door to the mind. You know, when you start talking, when you start writing, that's when I know what's happening in your mind. And so, in fact, these reflections tell me something as to what did go through, what didn't. But the last thing I want to mention is, if you look at these, and then I wish I can show you the other one. I can actually. Which is the kind of thing that people who take intro to AI write as the things that they got. There is a lot of overlap. So you at least know the buzzwords. You know some level of conceptual connections. Of course, algorithms are not going to come up in this picture anyway. But so I think that's sort of a good news. And then one last thing that, yeah, I think that's basically what I wanted to point out. And at that point, I am all done for this. Is there anything else anybody else wanted to bring up? If not, we can. Oh, I did want to mention one other thing, which is, okay. If you just say, in fact, if you just say AI, ASU, this course will come up. But this is my course from last fall that I taught. And this is the one that I'm suggesting you should be able to enjoy if you have nothing else to do or the class break. Many of you are asking, you know, where do I get the technical stuff? Essentially, these are all the lectures. And for every one of them, there's a video list and there's the slides. And in fact, you can, you know, watch the videos if you want. Of course, you can also take the actual course that somebody is offering, but that is certainly there. That's any of the topics, like, for example, Markov decision processes that we talked about, you know, there is an entire, you know, bunch of lectures on that. And similarly, infinite horizon, value and policy iteration, number 11, that's another kind of a thing. And the point about reinforcement learning is 12, 13, 14. At least you will see that the names are sort of making sense based on what we talked about. In particular here, theory of generalization learning and implication to neural network learning, that's the stuff that I was just talking to you about the double descent. Okay, so at least you kind of got some sprinkling of the ideas with respect to what happens. And so that's the place that I would suggest you look at if you want to learn more on any of the topics. Okay, and then that, and you should look at each other's reflections. I think that's a good thing to do. And if you haven't actually posted, make sure that you post your reflections. And today's class summary is still needed. I will post the summary requirement, and please do it. And I know that all of you who actually done the summaries, I know who spent more time doing the summaries, and that sort of obviously means something because you spent more time trying to make sense of what's going on in the course. Okay, so that's all I have. We're already way like 30 minutes late. But is there anything else that anybody wanted to ask? Okay.
I have a question.
Go ahead.
For TensorFlow, do you have any online materials that you would suggest us to start learning first?
No, I think you should play with the playground first. Again, doing the programming is different from understanding the concepts. The world is full of people who do neural network programming and don't understand the concepts, and also full of people who understand the concepts, don't know programming. But both are required to actually do useful things. To do programming, you know, there's tons of ways of doing it. I didn't obviously teach you anything on that in this class. Normally, when we have class, you know, in the 471, we'll have actual projects, and then, you know, we give all the instructions on how to use TensorFlow and, you know, or write the little piece of code that you want to do. So in fact, one of the interesting things is TensorFlow makes everything too easy. There's nothing that you have to do. All these people who say they're doing AI, it's like they switch on TensorFlow. That's it. There's really nothing. They don't even understand probably what gradient descent is. They don't necessarily understand the training error versus test error and the kinds of trade-offs involved in it. Because basically TensorFlow makes it so much easier. Like, you know, I showed you in the example, I showed you how to make a network by just clicking. The program version, which just basically allow you to declare n number of layers. Each layer has m number of units. And then it just randomly, and then the moment you do this, essentially one of the other great things is, as I said, basically the actual optimization is just gradient descent. And it turns out that doing the gradient descent involves chain rule in, you know, if you remember your differentiation. And the chain rule is what is called back propagation. And they don't even expect you to do that. They will just, the moment you define the network, it will essentially come with the back propagation routines. So you don't do anything other than switch it on. Okay, but the interesting question, of course, is you have to ask how many, for example, how many layers, why did you decide these many layers? Did you feel that this is a reasonable fit to the data? The kinds of things that we're talking about is what mostly people do in actual industry in trying to do this stuff. Because the actual, at least the beginning stages, writing of the code is made too easy. In the good old days, people would do assembly level programming. Now anybody can do anything because everything is high level. And in fact, you know, the playground makes it even more high level because you just click and, you know, make the network. But something like a GPT-2 network, obviously I can't click because there are 13 billion connections or something. So it's not going to be seen on the, you know, on the screen. So there is an obviously easy way of specifying in a programmatic form. But to even get there, people need to know what programming is. Some of you have background, some don't. So I didn't go into that at all. I do realize that some of you, I think a majority of you are the, you know, the first year students, but some of you are actually were expecting this to be a mini 471, and it is a different kind of a mini 471. It is a conceptual version of what you will learn in 471, as against the prefix of the first 3 weeks of classes of 471. Okay, that's what winds up happening. Anything else?
I had a question,
Yeah.
and it might just be like, maybe I'm just a weirdo, but I know you were talking about how things in the future we discount. But I was
Mhm.
thinking about like how we consume maybe like entertainment or something. Like you don't want to like watch the spoils, you want to like watch the whole movie and then like boom, a spectacular ending. Or like if I'm playing a game, I don't want it to be like click a button and I win. I want like a little bit of challenge. So maybe I'm just like a stubborn weirdo. I'm not quite sure, but like.
No, I think, again, these are theoretical models, but in general, I'm pretty sure that even you, I mean, you clearly can understand if I'm going to offer you $10 now or $100 10 years from now, you would prefer $10 now, right? Unless if that's not the case, let's have a nice, interesting conversation, because then it's not, suddenly you are unique that you prefer $100 10 years from now than $10 now. Okay. But within the smaller time frames, I mean, there is again there's this idea that you have, which is you are getting by actually what you're talking about is that the enjoyment you get from the partial movie is not as much as seeing the whole movie and so you don't want the spoilers. You don't want me to tell you what happens at the end of the movie. But that's different from saying, I would actually prefer to be complete pauper right now, not have any money, with the possibility that about 35 years to 79 years from now, I might be a billionaire. Most people don't have that discipline. And in fact, people who actually make lots of money, do actually go through this. They have this discipline to kind of hold out for the big payoff at the end. So maybe you will be the next Bezos, you see, and that would be a good thing in a sense that you actually have. In general, I consider the ability to appreciate delayed reward is a high mark of success in the current society that we have built. Okay, many kids don't understand what's the point in going through 20 years of schooling when they can start already flipping burgers right now and make real cash. Do you understand what I'm saying? And it's very hard for people. I mean, so to some extent, what we teach to people, maybe by example, is this appreciation of the ability to, the appreciation for the delayed reward in general. And if you already have it, you're in good shape. But of course, anything can be overdone. You can say, I am not at all interested in rewards at all. So delay can be infinite. In which case, I don't quite know, that would be a strange, value system, except it's your value system. In fact, there's this funny joke that maybe it's worth remembering, what's saying. So these Americans go to UK in London, and they basically are trying to buy some tickets for some attraction, and there's a kind of a queue. So it's already a long queue. So they stand at the end of the queue. There's this British family in front of them, and then so basically, as soon as the British family then comes to the cashier's window, it says, hey, let's go stand in that other queue, and they move. And these Americans are thinking, what the heck are these guys doing? It's completely irrational from the Americans' point of view, because Q to you may be a negative, necessary evil to get the positive of getting the ticket. But the stereotype is the Britishers like Q so much that they actually associate value to just standing in the queue. And if you want to do that, then the best action for you is to stand in the next queue instead of this. That's exactly what, you might think of this as, oh, Britishers as Americans. But what do you think people in your high school or grade school who dropped out after high school or grade school are thinking of you? They are thinking, at least we got finally done with high school and we are off to enjoy life. And Catherine is still taking one more school. She stepped in one other queue. She's clearly getting some, masochistic happiness Remember, the word masochism makes sense. What general people think is pain, masochists consider pleasure. Do you understand what I'm saying? So in a weird way, all of us are masochists in our own way, because our values don't make sense unless you are like straight down the middle, mainstream person, which I hope nobody is, because they're very boring. Everybody has quirks in their value system. And so it looks like, for example, like I was just saying the other day that recently the AAAI, this large conference got done, and these two people had to deal with 9,000 papers, which have to be reviewed. Each paper has to be reviewed by 4 people. So they had 10,000 people write reviews for these papers, and they had to basically, coordinate all of these people. Okay, and then decide which papers get in, which paper get out, which papers don't get accepted. They're not writing the thing, but they're getting everybody to work on this. The people running the show spend humongous amount of time. Basically, they lost the last 6 months of their lives. Their wives and husbands and whoever else don't know they exist anymore because they haven't seen them. What do they get out of this? Zilch in terms of money. Nothing. They basically get happiness here because they think by doing this, they're helping the community. And of course, there is some indirect thing, because now we do then tend to say that we made the society in such a way that the program chairs who do this, we have a lot of respect for them. We'll give them, we might have goodwill for them. It will help, slowly in some other way. If you start saying, what's in it for me, you will never do like running the program chair thing. You would never necessarily do even, standing in the queue or doing, graduate school, etc. And, much of this, in fact, and there's this other discussion a couple of weeks back where basically people, I may have mentioned this too, that people shouldn't do science and grad school because there is like a big payoff at the end. You better do it because you like standing in the queue. You better do it because you like the process. You like the process of science. Because I can't actually sit down here and tell you that by doing grad school or even by doing college, you would be guaranteed to be more successful in some random metric you define in terms of, average amount of bank balance for the next 25 years than your bozo friend who dropped out of elementary school. That bozo friend may well be laughing all the way to the bank. As I mentioned one of the times, all the people who have made all these big companies dropped out of college. They didn't even complete college. Gates dropped out of college. Zuckerberg dropped out of college. In fact, I think Page and Brin are the only losers. They actually completed PhD before doing the Google. Eventually, it is because you have happiness on that. And the technical connection I want to make is, in AI, everything is with respect to your personal values. Remember, Bayesian probabilities allow you to say what is the probability you associate with events. And you are also allowing what is the value and reward you associate with different states of being. Then it looks as if anything is rational. No. If in fact you like standing in the queues and you decided to buy the ticket and get out of the queue, you are being irrational. If you in fact believe that tomorrow in Tempe, it's going to rain very badly, and then you wake up and get out without holding an umbrella, you're being irrational. Be consistent with your beliefs and your values. That's all AI is going to tell you. That's what any agent does. Okay? Anything else? Okay, guys. So enjoy your break. Do make sure to write the summary. And also, before I forget, I don't know how many of you completed the Honors College asked me to tell you to complete the course evaluation thing that all of you have been sent. I think the last time I checked, 6 out of 21 completed. So the rest of you, if you're not one of those 6, please complete. I won't see it before your grades are all over. It will be useful to know whether it's worth doing. I did this on a lark. It's like I never did this and I don't have to do it as I told you. And I'm wondering whether or not it's worth doing it again. So that would be a useful feedback to get. Okay, you don't have to tell me now. You should, that sort of thing that should be separated, because clearly you can't say it's not useful when I'm about to give you a grade tomorrow. That's not going to be good for you, right? So I think you should be happily saying the truth, you know, in this anonymous feedbacks. Good luck and enjoy your break. Thank you.
Thank you.
So much,
Thank you.
Professor.
Thank you. Yeah, I missed the announcement about the reflection thing, but I'll do that tonight.
Please, okay. Those of you who didn't complete, make sure that you do, please.
Okay, thank you.
I guess.